Good morning, good afternoon, good evening, good night, good whatever time it is where you are. Welcome to today's Math Minute, the only Math Minute guaranteed to be today and guaranteed to be no more than 10 minutes long. This is a follow-up video, perhaps one of two follow-up videos, a three-parter maybe, based on the last video we did on greatest common factors. So one thing that I did in that video is I took these expressions. You can check out the video if you want. I was looking at how to find the greatest common factor of, in this case, two expressions, but it can actually be any number of expressions without actually just listing every single factor and then finding whichever one is in some sense the greatest. I say in some sense because if I don't know what these variables x and y are, how am I supposed to quantify what we mean by greatest? I can't just use the magnitude of the coefficient of whatever the greatest common factor has to be, right? In other words, basically, I can't just say, oh, 6x is bigger than 7y or something, right? I need some other way to measure what we mean by greatest common factor. Even if we could ignore that, though, probably I don't want to sit here and list out a bunch of factors if I don't have to, right? I want to find some other way to figure out what the greatest common factor is. And so I mentioned, well, 18xy squared, I happen to know, has 36 factors. If we were to start to list them all out, 1 and 18xy squared, 2 and 9xy squared, but also things like x and 18y squared, 2x and 9y squared. I can do this, and I'm going to end up with 18 different rows of factors here. Again, if I can avoid that, I really want to. Same thing with 30x squared y. In that case, we actually end up with 48 factors. How is it that I know, without actually listing them all out, that 18xy squared has 36 factors, or 30x squared y has 48 factors? Let's consider just some numbers. It's a little bit easier, I think, to see this with some numbers. Let's say we're looking at 72. And we want to know how many factors 72 has. Now, for now, let's stick with the traditional method of just making a big table. And then we'll see if maybe we can figure out what's going on here. So 72 is, of course, 1 times 72, 2 times 36, 3 times 24. We're just going down the list, dividing these in. If they divide evenly, that's a factor, right? So 1, 2, 3, 4 all work, but 5 does not, because 5 does not go into 72 evenly. 6 does. It's 6 times 12. You'll notice as we move down the table, if we're doing it this way, the numbers are getting closer together. And that's good because what we want to have happen in a moment, 7 does not work, 8 does work, and the very next one is 9, which means at this point I no longer have to keep testing. Anything 9 and larger, if it were a factor, would appear on that other side of the table. So what do we have here? 1, 2, 3, 4, 5, 6, 12 different factors, right? So 72 has 12 factors. What I want to do is write these same factors, but I'm going to write them a little bit differently. One thing we said when we were looking at the greatest common factor in the last video is that you can use prime factorizations. If we do a prime factorization for 72, the little Christmas tree looking thing, what might we say? Well, we might go with 8 times 9. That's a pretty common way to get to 72 via multiplication. Neither 8 nor 9 are prime, of course, so we have to keep going. 8 is 2 times 4. 2 is prime, so that branch is done. 9 is 3 times 3. 3 is prime, so that branch is done. And then the 4 itself is 2 times 2. So there it is, right? This is 2 times 2 times 2 times 3 times 3. Or if we write it in exponential notation, 2 to the third times 3 squared. If we come back up to this table and we want to write these same factors, but we actually did a prime factorization for all of these, you would end up noticing something interesting. Let's start with the 2. 2, of course, is 2 to the first. And what's 36? 2 squared is 4 times 3 squared is 9. And so that is the same as our 2 times 36 over on the left table. Let's do the same thing for the next row, 3 times 24. 3, of course, is 3 to the first. 24 is 8 times 3. That is, it's 2 to the third times 3 to the first. Do the same thing for the next row, 4 and 12. So that's going to be 2 squared. No, I'm sorry, 4 and 18. So that's 2 squared, and then 2 times 3 squared. And let's go ahead and finish out the table. 72 itself, of course, is going to be 2 to the third times 3 squared. That's what we saw in our prime factorization down here. And 1 for now, let's just kind of leave alone. We don't really know how to state that the same way that we've been stating these other ones. I mean, I guess its prime factorization is 1, but that actually doesn't really make good sense. 1 is not itself a prime number. So let's just kind of leave it alone for now. What do you notice about the table. Presumably, you can see, oh, well, these factors are all just various combinations of 2's and 3's, which of course makes sense because 72 itself is just a combination of some number of 2's and 3's. But there's actually even a little bit more to it than that, right? Because these rows were themselves just ways to come up with 72, in each case, I end up with the proper numbers of 2's and 3's across the whole row. So I can see here 3 2's, 1 on the left, 2 on the right, and then 2 3's. And that's what 72 is, so just 3 2's and 2 3's in various combinations. And it's that phrase, in various combinations, that reveals to us the way we can tell how many factors some number has without actually computing what all of those factors are. So in each case, for 72, you can think of what we're doing as we come up with any given factor as just choosing some number of the 2's and 3's that we know go into 72. So I'm going to draw 2 blanks, and I want us to think, okay, what could go in the first blank if this blank is devoted to 2's, and then this blank over here is devoted to 3's. And remember, let's also think about what is available to us. 72 is equal to 2 to the third times 3 squared. 2 to the third, that means we have 3 2's to choose from. We could use one of them, we could use 2 of them, or we could use all 3 of them. So that looks like 3 choices, right? And then the 3's, what could we do there? Well, we could use, once again, one of them, or we could use 2 of them. And so that looks like 2 choices. And for those of you who are familiar with the fundamental counting principle, you know that when we have scenarios like this, some number of choices by some number of choices, it is the product of those number of choices that tells us the total number of combinations of elements, whatever the elements are. In this case, the elements, of course, are the numbers 2 and 3. So it looks to me like I have 3 choices for 2's and 2 choices for 3's, and of course that ends up making 6. Well, there it is, 6 factors, right? That's what we said. No, we said there were 12 factors of 72. Why are we only getting 3 times 2 equals 6? What's gone wrong? And wait a second, is it true that we always had at least 1 2? Or that we always had at least 1 3? Are those in fact our only choices? Oh wait, no, they weren't, right? Sometimes we had no 3's at all. Sometimes we had no 2's at all. Sometimes we even had neither 3's nor 2's. And that tells me, oh, that's what's going on with 1. Those were actually the 0th power of 2 and 3 times each other. Remember, when you raise things to the 0 power, you get back 1, typically. So that 2 to the first, we could actually rewrite that now. We could think of that as 2 to the first times 3 to the 0. 3 to the first, we could think of 2 to the 0 times 3 to the first. And so in every one of these cases, you could make sure that you always have some representative of some number of 2's and 3's. It's just that sometimes that number of 2's and 3's is 0. And so go back to this list here, and let's add in our additional choice. Right now we can have a blank, no 2's whatsoever. So that's not 3 choices, that's 4 choices, right? No 2's, 1 2, 2 2's, or 3 2's for our factors. Same thing for 3. It's no longer the case that we can only choose 1 3 or 2 3's. We could also choose no 3's. So that gives us 3 choices for the number of 3's. And so now when we take that back to our blanks, it's not 3 times 2 equals 6. It's that 4 times 3 gives us the proper 12 factors that we know 72 has. So how could we state this in general? Let's go back to one of the examples we started with, 18xy squared, right? If we turn this into its prime factorization, that's 2 times 3 squared. I'm actually going to use powers of 1 just so we can see really what's happening here, times x to the first times y squared. We're going to look at the powers in each case. And because we can choose that many of the base, whatever it is, or none of them, our options are always one larger than the power. So we have 2 options for 2's, either 0 of them or 1 of them. three options for threes. It's just a coincidence that those bases are matching up right now. We could choose 0 threes, one of them, or two of them. Two choices for x's, no x's at all, or one of them. Three choices for y's, no y at all, one y, or two y's. And it is the product of those that tell us 18xy squared is going to have 36 factors overall. Let's do it one more time with 30x squared y. 30, of course, is 2 times 3 times 5. We have x squared. Let's make sure to use our first powers. And of course, we also have y to the first. So what are our choices? I look at the powers. I could choose no 2's or 1 2. That's two possibilities. No 3's or 1 3. That's two possibilities. No 5 or 1 5. That's two possibilities. No x's, 1x, or 2 x's. That's three possibilities. And then no y's or 1 y. That's two possibilities. 2 times 2 times 2 is 8, times 3 is 24, times 2 is 48 factors for that expression. I hope that has been helpful to you. The part 3 that I might come up with is sometimes for some odd reason we want to know the sum of all of the proper divisors of a number, that is all the factors that go into it other than the number itself. And there is a way we can connect this process to that sum, but that will have to wait for next time. Have a great weekend. I will see y'all in the next one.